So yeah, as I was introduced, my name is Raivo Kolde, and I'm an IT Academy associate professor here in the Institute of Computer Science. And my topic of research is all the Estonian health data and trying to do something useful with that. And I titled my talk with slightly pessimistically calling it Long Road Towards AI in Healthcare. And why did I do that? So first, I think you heard today already that AI has done pretty amazing things lately. So there are enormous advances. For example, there are AI models that generate really human-like text or code based on just short prompts. There are AIs that learn to play different board games on superhuman level without any human interaction, just by playing with itself. And there are lots of models for image recognition, segmentation, or image generation that do really amazing things. So here is an example of one of them from OpenAI that can generate a picture based on a description. Like, can you generate me a picture of armchair in the shape of an avocado? And here there are many different options for that. And how these algorithms all work is that they use a huge amounts of data and try to use that data to develop human-like intuition for predicting things. And healthcare seems like a very good application area for these types of models. First, there is a lot of data. So we recently obtained only a very small fraction of Estonian health records from Digilugu, and all these files were already 200 gigabytes. But for all people in Estonia, the size of the data is much bigger, and Estonia is a very small country. Imagine how much data there is in the electronic medical records in bigger countries such as US or United Kingdom or Germany. And there is even more medical imaging data in the imaging databases, like for CT scans and X-rays and MRI imaging and so on. So there is a lot of data, and there are also important questions that predictive algorithms can answer for you. So, for example, what will happen with a patient? What is the probability to get some disease or some bad condition? Or what is wrong with the patient right now? So can we take the symptoms and the medical history and come up with a good diagnosis for the patients? Or if we know the diagnosis already, how should we treat the patient? All these questions are somewhat questions for a predictive model. So AI seems to be in a good position to help with all these questions. However, the progress has not been so smooth as people hoped for. And I put up here some of the reasons why this might be the case. And I use this simple example of COVID-19 risk model that should predict the complications of COVID, or hospitalization, or need for intensive care for new patients, as an example. So these types of risk models are used in practice, for example, to identify people who should be prioritized for vaccinations or prioritized for treatment. And if you think about a model that is otherwise pretty good, but does really poorly for some subset of the population, then the consequences for doing poorly are pretty bad if these people are not vaccinated or they don't get the proper treatment. So the stakes in medicine are just much higher than, for example, playing chess. So if AlphaZero makes a bad chess move, then so what? Nothing bad happens from that. But in medicine, the stakes are higher. And it can easily happen that a model might do bad predictions, because the data that it uses for making these predictions can be in a constant change. For example, if we take the COVID example again, then the national testing regime in Estonia, originally, when the number of tests was very low, only very sick or very old people were tested. But gradually, as more tests became available, more people started to be tested. And imagine now if we use this original data from the beginning of the pandemic to build a risk model that has seen only very sick and very old people and tried to predict the risk for younger and healthier people, then we might get totally wrong results in that. Another problem is that although there is lots of data in the medical records, the data is not always high quality and things are not always recorded in consistent manner. So if we just use the data as it is, we might get a lot of weird results. And finally, even though we might have really large data sets, the big data becomes really small very quickly if you start looking at combinations of conditions. For example, if we want to predict complications for late-stage cancer patients who get COVID, then we might discover that in Estonia there was only a handful of cases and the algorithm, however good, cannot do much with the data to give good predictions. So large data only is not enough. We also have to know the data well. We have to know like how the data was generated, how the data was recorded, what are trustworthy parts of the data, which parts can we use, and also what are the limits of the data that we are using. So let's see how we usually use the data in a very rough schematic. So we have the raw data from, in Estonian case, from Digilugu or from Health Insurance Fund. And if we want to learn an AI model on that, we have to do some data cleaning in there, using all our knowledge about like how the data is generated and what's in there. And often it turns out that this data cleaning part, getting it into some usable format, takes quite a lot of time and a lot of effort. And this is like the main time sink when trying to learn these models. And the problem is that, yes, we get to know the data a little bit better by doing that, but this effort is essentially wasted if we try to learn another model or like do some other application, because the data needed for other applications looks different. And basically, we have to start from the beginning every time we develop a new applications or do a new study. So that's why we have adopted another approach. So instead of every time learning a new custom data structure, we have selected a data structure called Omop data model that can house all kinds of medical data. And where we can take any data set and convert it to this model and use this data model to learn our, do the clinical studies and learn the AI models. And this is actually, originally it's even more work, because there are more fields that we have to fill, there are more standards that we have to follow, and it's a lot of work to get the data into this type of format. But what happens when we get the data into this format is now that we have this nicely structured database where we have, for example, also extracted some values about the specific condition, now it's in a very good format already for all kinds of research. And we've experienced that like once we have done this step, then many more interesting questions become addressable using this data. For example, we started maybe learning AI models, but then we can see that we can also characterize the incidence, the prevalence of different disease conditions related to the disease. We can start doing economic analysis. We can start compare the treatments and so on. And while answering all these questions, so yeah, and now the initial investment into cleaning the data looks much better and the return is much higher. So instead of doing just one study based on all this work, we can do tons of studies based on this work. And of course, when we do these studies, we discover that like still there are more to do on the data cleaning and formatting side and the extraction side. So we can take this knowledge that we get while running these studies and go back to raw files and get even better data. So it kind of invokes this like virtuous cycle where the more studies we do, the better data we get. The better data we get, we can do even more studies and have a higher quality of results. So that's why we have really invested a lot of time to get this cycle running in our group. And one thing that we can do as well with this common data model is that we are not the only ones trying to get the data into this common data model. The same thing is adopted around the world, and now we can start using the work that other people are doing on the similar data, because the data structures are the same everywhere. So we can start adopting, for example, the machine learning models that are learned in other places, or we can start developing machine learning models together with other data sources in other countries. Also solving the problem that we don't have enough certain cases of patients, for example, because then we have much bigger pool of patients to draw from. And of course, we can start doing also all kinds of international clinical studies, comparing the countries and pooling the information. But all of this work also creates new challenges, and there is also a need for developing new research tools and methods to do research on this platform. So this is also something that we do. So to summarize, what do we do in our group? There are really like 3 arms that we are aiming for. One is to develop tools for information extraction from Estonian health data. So we're developing ETL tools that take the raw data to the OMOP model, but also free text extraction tools, information extraction tools to get out, for example, measurements from the free text and all kinds of other information from the free text. And finally, for the data that has low quality, we are also developing imputation tools, some of them that are deep learning based, for example, to reliably infer either smoking status or like body weight from the other medical records. And using this good data, we can start collaborating with clinicians locally and internationally. For example, we are looking Estonian COVID-19 risk models, but also we are characterizing the incidence and prevalence of prostate and cervical cancer in Estonia, doing drug utilization studies and so on. And also we are then developing research methodology and tools for all these questions. For example, characterizing patient trajectories and visualizing the results of the network studies. And you can see one of the visualizations just in there. So all of this is quite a lot of work. So I'm not doing it myself. I'm collaborating with other faculty here in the Institute of Computer Science, like Sulev Reisberg, Sven Laur, Jaak Vilo. And there are lots of people who are doing the actual work and doing the hard part of the work. And we are collaborating with the medical faculty in University of Tartu, Estonian Genome Center, Erasmus University in Netherlands, and with a bunch of projects. So that's it from me. Thank you for listening, and I hope you have any questions.
Thanks a lot. There is actually a question from the workshop asking about most interesting discoveries or results from your research in health issues, or more specifically the correlations that you found. Yeah.
So I think lots of these studies are still in the beginning, but I think there are like pretty interesting results for specialists where we are looking at, for example, drug use between different countries. So we have this one study where we are looking at asthma drug use in Estonia, but also we have the same study run in Netherlands and UK and Korea, and what we see is that we can find like really different patterns from country to country, and like it's for us at least it's pretty interesting. If you go through these differences with the doctors, you can start understanding like what are the different reasons that like guide the drug use in different locations and so on.
All right, and just got another one. What ETL tools do you use to clean the data? And how much time goes on extracting and cleaning the data compared to the other parts?
So all the data lives us in we keep the data in the in a Postgres database. So it's mostly different like SQL scripts that we're using in there to clean the data. There are some like specific ETL tools also meant for this process. If you start from the beginning, for example, just to map the data that you have and map it between the with the database structure, but like I think we are gotten far enough with the process that we have developed our own like approaches for these things, and our questions are very specific, not very generalizable anymore for like general purpose tools. But it's very hard to estimate the percentage because like there are few people who are only doing that part of the thing, and they have always more work to do than they can do right now. But everything they do enables other people to work on other things on the data already.
And since we have a few more minutes in this session, I would like to ask another question. This is about the personal medicine. Obviously, is a hot topic at the moment, and people, especially in the Western world, would like to know more and more about themselves and how far are we from, let's say, a complete or comprehensive prediction, AI-based prediction on myself, for instance? Say you have my medical records, you basically, I don't, but many people wear Apple Watch with many sensors. So is it like possible to combine all sorts of data, maybe even a genomic data, if my genome is ever sequenced, and then do like a prediction that I have X% risk of this disease and I should do this or that?
So I think that's why I titled my talk "Long Road Towards AI." It's because I think it's a really long road ahead, and I think there are no real shortcuts that we can take. That like we just feed all the data to the machine, and the machine tells us the right answer. I think there are like a lot of work has to be done on the data side to really understand what's in there and like build up these solutions like one by one, and like but hopefully in some time we can get there, what you were describing.
All right. Yeah, anyway, thanks a lot for the presentation. It's actually very thematic in the COVID period.